Okay, so this problem is the one with a man and his toboggan, and he's going for a sled ride. And he's at the top of a hill, which is 60 meters vertically above the valley floor. So I've already drawn a little diagram here. So he starts up, say, here, and that vertical distance is 60 meters. He runs and leaps onto the toboggan such that he and the toboggan have a speed of 5 meters per second when they start their journey. So if this is them, then they have some little amount of initial velocity, and that's equal to 5 meters per second. And he slides down into the valley and then up a hill on the opposite side. And A asks if the hill on the opposite side is 62 meters tall. So I'll get up here to the top, is 62 meters. Does the man and his toboggan make it to the top? And then you're supposed to state yes or no and then show your calculation. And you may assume that the work done by non-conservative forces is 0. So in reality, of course, there would be some friction between the toboggan and the snow. But we're saying, we're going to call that negligible for this calculation, just to get the basics. All right. Well, if that's true, if the work done by non-conservative forces is 0, then mechanical energy is conserved. And that means that his initial mechanical energy has to equal his final kinetic energy. And initially, we have both kinetic and potential energy, right? I suppose this depends on where you set your reference level, but I'll set the reference level sort of where we're measuring everything from, which is the valley floor, though you're free to set it, again, wherever you'd like. So we have mgh0, and we have 1/2 mv0 squared. And for the final mechanical energy, well, basically we want to know if he gets there. And sure, if he was still moving at the top of this taller hill over here on the right, then he'd clearly make it to the top of the hill. But that would mean he'd had all that extra potential energy. In addition, he would have a little bit more kinetic energy. So we're saying, what's the minimum amount that he would need, okay? And we're just trying to figure out, does he make it to the top? And so we can assume that if he makes it to the top, he's just going to creep up to the top. And so this term that would normally exist, okay, if he was moving, is going to be 0 for us. And we're going to do this for the potential energy. Now, if we look at all of these terms, well, we want to see how high he goes with this initial amount of mechanical energy. So we're going to solve for this, and if it's greater than 62 meters, then he makes it to the top. And if it's not, then he doesn't. And a couple of things, we don't need to know his mass. We don't know his mass in the problem, so it's good that we don't need to know it because it appears on all of these terms. So we can divide both sides by mass, and that goes away. And then we can just solve for HF by dividing both sides by G. That gives us H0 by itself plus 1/2 V0 squared over G. And if you put all of that in, you should get just a little bit less than 62 meters. Let's see if it works out. So we get 0.5 times 5 squared, and then dividing by 9.8. And we add that to the initial height, and we get that the final height that he could achieve is 61.3 meters. He doesn't quite make it to 62. So the answer for this version of this problem is no, he doesn't make it. I think for the other version, if you do the same calculation, you find that he does make it, and that's because he has a slightly greater initial velocity. Now for B, we're asked, okay, well, let's see what minimum starting speed he would need to make it to the top of the opposite hill, right? So he can't have any more potential energy. He's at the top of a 60-meter hill, but he could really go for it and get moving faster when he starts his run. And so we want to figure out what that is. And basically we're going back to the same set of equations, right? We're going back right to here. Except here we're gonna assume that this final height is 62 meters, like he makes it. We're trying to figure out what velocity he would need to start with to get to that 62-meter height. So that is no longer unknown. We know that in our calculation. And the thing that we're looking for is what this initial velocity would have to be to make that happen. So we cancel all of our masses again because they appear everywhere. And we can do a couple of steps of algebra here if we like. Divide everything by 1/2, which multiplies everything by 2, and then take the square root of everything. Just grouping things a little more conveniently here. And so you should get right about this many meters per second, okay? So 2 times g, so you get 19.6, and then you multiply that by 2, and then you take the square root of it, and you should be okay. All right, so that's the minimum speed he would need. Anything more, of course, would mean that he still had some initial, or kinetic energy rather, when he gets to the top of the 62-meter hill on the opposite side. All right, there's that one. On to the next.